in smaller classes you have learned. So now introduction to fluid mechanics. Now what is fluid? Most familiar definition is that it undergoes deformation easily on application of an external pressure. It is okay. Now if a shear stress is applied to a solid, suppose. Now consider action of shear stress on a solid. If we are taking a practical example such as cutting of vegetables, all of a sudden it undergo deformation, and that is and if we are considering same with, that is, if you are applying shear stress on a fluid, it undergoes deformation continuously with the time. For example, a river flowing and it experiences shear stress from its own bed, and its deformation is continuously changing with time, and it is because these fluid molecules are resisting the same. The property by which the fluid molecules can resist is called viscosity. So it is a term for the easiness with which it can flow, is what a common man says, but actually it is the resistance offered to shear stress. So here if you are seeing a cross section of river flowing is shown, the velocity, it's not uniform throughout the depth. It is maximum near the surface and it is continuously decreasing towards the bed because of this same shear stress offered by the bed. That is what shown in this figure. So here we can get into a new term, which is velocity gradient. Velocity gradient is nothing but that is the change of velocity. Now the velocity is horizontal, and it is varying with respect to the vertical axis. So if I am saying the change in velocity as dv, it is varying in y-axis. Suppose this axis is y. So this dv by dy is nothing but velocity gradient. Now, so this velocity gradient, shear stress, viscosity all have some connection in between. Now we'll move on to that thing. So we have come to know about one of the properties of fluids, viscosity. So you should be familiar with some properties of the fluids, which first one is mass density. Mass density is nothing but mass per unit volume. So its unit can be kilogram per meter cube, and specific weight this mass density is denoted as rho, and specific weight is weight per unit volume. So its unit is Newton per meter cube, and it is denoted using the letter omega, rho g, which is equal to, this should be equal to rho g. Okay, it's similar to small w, looks like. Capital omega is this one, I think. Okay, next, relative density. Relative density is the ratio of density of the fluid we are considering to that of water. So rho of whatever fluid we are considering divided by rho of water. And viscosity. Viscosity we have already told. It is the resistance to shear or angular deformation, and it is property by virtue of which it offers resistance to the movement of one layer of fluid over the adjacent layer. And this property, the fluid possesses this property because of intermolecular cohesive force only. That is, you might have come to know about these cohesive forces and adhesive forces in smaller classes. This cohesive forces is the force of attraction between two alike molecules, and this adhesive force is force of attraction only. Okay, if between dissimilar molecules it is cohesive force, and if between similar molecules it is cohesive force, and if between dissimilar molecules it is adhesive force. So whatever fluid we are considering, a layer of it offers resistance to the adjacent layer because of the attraction, this attractive force, cohesive force. That is, a fluid layer, when it is moving over a river bed, suppose a river flowing, and from its river bed it is experiencing some shear force. So at the bottom of the river bed it is dragged backwards, and the layer of the river, this bottommost layer will be pulling the layer just above that again backwards. So that property is viscosity. So you should be knowing in detail about this viscosity and Newton's law of viscosity. So I have already told this viscosity and how it works on and all, giving the example of river only. That is, velocity decreases towards the bed, and this Newton's law of viscosity explains relation between those three terms which I have told you in the beginning. They are shear stress, dynamic viscosity, shear stress, dynamic viscosity, and velocity gradient. So as per Newton's law of viscosity, this shear stress is equal to dynamic viscosity times velocity gradient. That is, this shear stress is proportional to velocity gradient. Intensity by which this velocity decreases to river bottom is proportional to shear stress. As the shear stress increases, this velocity will be suddenly decreasing, and because of what? Viscosity only. And it is I have told you this as dynamic viscosity because while defining viscosity we will come across two terms. They are dynamic viscosity and kinematic viscosity. Because this dynamic viscosity, we have told it is the constant of proportionality between shear stress and velocity gradient, and it's if you are looking into the units, this shear stress is Newton per meter square times or divided by velocity gradient. So it will be so this is dynamic viscosity, and kinematic viscosity is dynamic viscosity divided by density. So what we will be getting? Here Newton second per meter square is the unit of dynamic viscosity, while mu by rho, Newton second per meter square. Now rho is mass only, so force divided by, if I am giving it to I'm sorry, kilogram per meter cube. So Newton by kilogram is what? Meter per second square. So meter square, so you will be getting it to meter square per second. So that term is kinematic viscosity, which is independent of any force term or unit of force. Now again we will move on to Newton's law of viscosity. Now this law is not Newton's law of viscosity is not applicable for all fluids. It is applicable for some fluids like commonly what we see: air, water, light oils, gasoline, etc. So those fluids which obey this law as it is are called Newtonian fluids. Newtonian fluids that obey Newton's law of viscosity, that is, shear stress is proportional to velocity gradient or is equal to mu times dou v dy, which is examples include air, water, etc. And now comes the other category, non-Newtonian fluids. Now we will see some examples. There are some further, this can be further subcategorized, this non-Newtonian fluids. We look into some examples, like, see, the first figure shows ghee, butter. First figure shows butter. See, when we are applying shear stress, this shear strain takes place at a larger rate, or there what we can see is tau equal to mu dv by dy is for normal fluids like air, water, etc. But for butter like things, this tau is proportional to dv by dy raised to n, where n is greater than 1, because the strain undergoes at a larger rate, at an exponential rate. Or if we and see, the second figure shows paper pulp. For paper pulp, what happens is, this shear stress, when we are applying shear stress, it undergoes shear strain at a logarithmic rate, if I am saying. That is, it is proportional to dv by dy where n is less than 1. Other examples of this include blood, suspension, paints, rubber, etc. See what happens there. when we are applying shear stress, this velocity gradient has a greater shear stress is required for causing a smaller change in the velocity when we move downwards. Other examples include blood, suspension paint, rubber. They require greater shear stress. And other types are also there. I will show you. See. The first figure shows here drilling mud. See there what happens. It has already some shear stress as its own, on its own. So what we can say, this shear stress is equal to some constant into velocity gradient raised to n plus some constant, another constant, that is this B is tau initial. It already possesses some shear stress on its own. Okay, after so whatever shear stress we are applying is supplement to that, and this n is equal to 1 also, so we can just neglect that n. That is, they are linearly proportional. They are Newtonian fluids only, but the problem is if we are neglecting the initial shear stress. And this one, what I have intended to show you is lipstick only. These kind of fluids are known by thixotropic fluids. Another example include printer's ink, and they are time dependent fluid, that is viscosity depend upon both shear stress as well as the duration of application of the shear stress. So viscosity increases or decreases with the time. For example, this printer's ink only. So these are the types of fluids, and thixotropic, this equation is represented as tau is equal to, it also possesses some initial stress plus mu into dV by dy raised to n. Okay, and next I will show you the graph showing all these kind of fluids. This pseudoplastic fluid, they are thixotropic fluids only. This pseudoplastic fluid, actually this is pseudoplastic. Pseudoplastic fluid examples also include paint and enamel. They don't possess initial shear stress on its own. So when subjected to high shear by brush during application of paint, apparent viscosity is reduced. The paint covers the surface smoothly and brush marks disappear subsequently. So that is what they have used. That is, after some time brush marks disappear. So there is some influence of time also. So they are called pseudoplastic. Initially we think whatever shear stress applied, when we apply whatever shear stress, they undergo some deformation for permanent, we may think, but it is not that. After some time the pain marks disappear. So with this I am concluding about Newtonian and non-Newtonian fluids. I have discussed the examples also. So this is Newtonian fluid. Bingham plastic fluid I have already explained. They are drilling mud. Example, they are we may think they are Newtonian fluids, except that it possesses initial shear stress of this much. So they are called Bingham plastic fluid. And pseudoplastic with the initial shear stress is thixotropic. Pseudoplastic, this paint without initial stress. But the other one example is lipstick.